Welcome to this session of Shadow the Scientist, investigating the collisional outcomes of asteroids in the main belt, featuring research being conducted at the NASA Infrared Telescope Facility. My name is Jamika Marshall, and I am pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity and STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. The NASA Infrared Telescope Facility, also known as IRTF, is one of the telescopes comprising the Mauna Kea observatories on the Big Island of Hawaii. The IRTF is a 3.2-meter telescope optimized for infrared observations. The observatory is operated and managed for NASA by the University of Hawaii Institute for Astronomy, which is located in Honolulu. The IRTF is a classically scheduled telescope. So to make the most efficient use of telescope time, multiple observing programs are often scheduled each night. 50% of the IRTF observing time is reserved for studies of solar system objects. In this session, we have the privilege of shadowing astronomer Bryce Bolin. Now, Bryce is a NASA postdoctoral program fellow at the Goddard Space Flight Center. In this session, he will be studying the remnants of asteroid collisions in the main belt and working to determine their surface compositions. Along the way, he'll explain how using NASA's infrared telescope facility will help astronomers better understand the origin of meteorites, as well as how they're transported from the main belt to our planet Earth.
So yeah, welcome. We are in the process of setting up the telescope for our observations. Can you all see this screen right here? I'm going to move these windows around a little bit. So I'm going to put the all sky camera right here. So this is kind of how the setup for the telescope looks right now. I have 3 windows right here that are allowing me to operate the instruments, and at the same time I am also looking at a 4th window right here that's looking at different weather conditions. So this is a kind of a meteorogram that shows us the temperature, humidity, pressure, wind speed. We have another window here that is giving us seeing measurements, basically the sharpness of our images. And we have all sky cameras. The main one that I use to see what's going on is this all sky camera right here. It's pointed directly up. Right now it's pretty clear. Brian, would you say it's a pretty clear night so far? Yeah, it's pretty clear so far. So just give a quick introductions for everyone. My name is Bryce Bolin. I am an astronomer at NASA Goddard Space Flight Center. We have some guests with us here. We have Brian is the telescope operator. Can you all see him over there? He's waving hi. He's the one who's actually running things here. He's the one actually driving the telescope, entering commands, focusing it. So he's slewing to a target right now where you're gonna focus the telescope, right?
First thing pointing. Yeah,
Point. So he's gonna do a pointing check to make sure the telescope is pointed accurately at where we want it to look. And then he's gonna focus the telescope so our images are as sharp as possible. And then we'll do some science observations, but we're still kind of just setting things up right now. We have some guests. Francesca, sorry to bother you, but would you like to introduce yourself? Come here and say hi. To say a little bit about what you do. So this is Francesca. She works here too. And would you like this? She's a night attendant, right? Are you a night attendant?
Yes. Our titles have changed. We're now called Observatory observation assistance.
Mhm. Okay, and so she was filling up the telescope. So the telescope needs all these cold chemicals to operate, liquid nitrogen and what other cryogen you used? You were using liquid nitrogen, right?
Yeah.
So it's cooled to about minus 373 degrees Fahrenheit. And we need, so she puts this liquid nitrogen in all the instruments to keep them cool for us. And so she was out there doing that earlier. So all the instruments are running cool, so we can take pictures in the near-infrared sky. And then we also have some guests with us. Would you all like to introduce yourselves? We have Lieutenant George Denove is from the U.S. Navy. Where are y'all all Navy or Army or all Navy?
Yeah.
So, so y'all are coming from where, Pearl Harbor or?
Pearl Harbor.
So we have some people from the U.S. Navy. It's Memorial Day. So we should thank our service people for their work. They and as well as to the people here who make all this telescope stuff work. We couldn't do all this without them. So round of applause for them. So yeah, here's the all skies camera right now. So you can see here, this is the east, point east. I'm sorry, this is west and this is east. So there's still a little bit of sun in there, but the stars are really shining brightly. They're really coming out nice and bright. Let's look at the seeing. So I'm not sure how good these seeing measurements are, but we have 0.46, 0.3 arc second seeing. That's really good.
Definitely not that.
Yeah, well,
It's variable and probably.
well, that's still very good. So Brian's focusing the telescope, and he's doing these measurements right here. So he's focusing the telescope on a star right here. And he's actually able to determine how sharp the images are. So it's looking like it's is that, so you're changing the angle that you're measuring that slice, and it's looking like it's changing. The angle has to do with the focus, or
That's just a variable seeing, and you're gonna get a different cross line for that depending on the angle that you cut the star with. I don't totally understand how it works, but it does.
okay. So we're
What
still,
I is just trying to get this this seeing figure to the lowest possible figure,
okay.
lowest on average, because I was seeing 1.0 and 0.9 on my last focus figure. It's not quite as good as this one, which is giving me an average of 0.7, 0.8, possibly 0.6 on if there's
Okay.
on average, this focus figure at 0.25 is going to be better. I guess it made our seeing at 0.8.
At 0.8, that's still pretty good seeing. Most observing sites in the United States mainland, like we're talking like in Arizona, New Mexico, Southern California, they're going to get seeing around 1 to 2 arc seconds. Mauna Kea, you usually get below 1 arc second, so you usually get it can be a factor of 2 or better. So because the air up here is very clear, so we're measuring we're focusing the telescope and measuring the sharpness of our images. Are you doing the seeing check right now? I mean the pointing check, or
Pointing first, otherwise we wouldn't see a target there. So
Okay.
pointing, just finish up the focus. I'm spooling back to your target.
okay, so we're gonna do our first target here. So let's see. So we're gonna look at a star that is like our sun. We're gonna get its spectrum. I'm gonna show you all what that looks like. So this is a special kind of infrared telescope. It takes pictures of the night sky, and that's what we're seeing right here in this top right window right here. Sorry if I'm messing that up, Brian. I'll move my cursor.
No, you guys are good. You're good to go.
Okay, great.
I just established the target.
Okay, great. So, all right. So I don't think we need to use Morris. So this is Guide Dog. Okay, so I'm gonna pull up your cheat sheet. So Brian made this has a cheat sheet that goes through the process of setting everything up. Well, I have it here in my notes. So Brian's cheat sheet for setting up all of these different things. Step-by-step process. All right, here we go. So, all right. So the first thing that we do, so I have to get the camera ready. So this is a special telescope that takes images and spectra. I'll tell you all a little bit what a spectra is, but right now we're going to get the camera set up so it knows how to guide on our target. So I'm changing the filter right here. So this is an infrared telescope. It looks at wavelengths that you can't see with the human eye. A human eye is visible wavelength, but what we're observing is near infrared, so a little bit longer wavelength than what we can see with the human eye. So I'm going to take the shortest exposure possible. And okay, so that was a test image. So the first thing that we do is we align the telescope. We align the slit to the parallactic angle. I'll explain what the parallactic angle is. That's the very first step. We want to align the slit with parallactic angle. Basically, we want to have our spectroscopic slit pointed directly down towards the horizon. And I'll talk a little bit why we do that. And then we click on auto guide box setup, and we take another AB pair, beam pattern AB. So the way it, so in optical wavelengths, the sky is pretty clear. Humans evolved to see in the optical because the atmosphere was clear in those wavelengths. But near infrared wavelengths, the sky is actually very bright. So you have to subtract, you have to take two images, and you have to move one image a little bit differently from the other, and then you have to subtract from each other in order to see stuff, because the sky itself is pretty bright. There's also heat from the image itself that causes this. Take AB pair and window 2, set the C buffer. Okay, we are good here. And then you draw a line from the A detection to the top box. Okay. So basically, I'm telling the telescope to put the stars on these little boxes right here. And then see that working. So we offset the telescope. So now we should be good for guiding. We want to use bright guide mode, method 8B, correct to TCS, and we'll hit go. So now we're just going to make sure that this is guiding here. So in this window right here, so this black line right here, this gray line right here, that is the slit. That is the spectroscopic slit. So we see that our star is directly underneath that spectroscopic slit, and the telescope software is keeping that star directly underneath it. So we got it where we want it. So now we're going to go to this bottom left-hand window right here, and this is the actual spectrograph setup. So this is a very bright star. So I'm going to do 2 coads of 5 seconds. See how that goes. And so now that we have the spectroscopic slit on top of the star, I'm going to just start taking data. So we have the 0.7 dichroic in there. So we're going to take data from 0.7 microns all the way to 2.5 microns. We have the order sorting filter open. The parallactic angle is, we have the slit aligned to the parallactic angle. We have our slit at 0.8 arc seconds wide. We're using the prism. And I think we're good to go. So I'm going to hit go here. So we're going to take a spectrum right now. Okay. So I'm doing, I'm looking at the data as they're coming in. Brian, do you know why we have this weird pattern on buffer C
Guide dog, big dog.
on Big Dog? Yeah, if you look at it, it's got the cross disperse. So we're in prism mode, and it has this cross disperse kind of pattern.
Wait, we never took the beat.
Oh, that's right. We're not. Okay, guys, that's AB pattern. Okay. Oh, actually, this reminds me. So we are taking some science, some science stuff right now. But I think what we want to do is I want to show you what the spectrum looks like. So we can actually, I can show you in real time what the spectrum looks like, but we need to do some cals. So is it okay if I do some cals real quick? So I'm going to stop the guiding. And
For all of you that are with Bryce, this is what I.
okay, here we go. I'm gonna run some calibrations here. So this way we'll have the files, the data necessary to calibrate the data, and that way I can show you what the spectra look like in real time. So now what the instrument's doing, it has all these internal mechanisms that allow it to do a couple of calibrations. One calibration is called flat field calibration, because the camera for the spectrograph has these artifacts in it, just due to differences in the sensitivity of the camera over the entire detector plane. And so doing a flat field correction allows us to remove those. And then we're also going to do what's called a wavelength calibration. So in a spectrum, we don't know exactly which data points correspond to each wavelength. So what we do is we take a spectrum of some chemicals that have known emission features at specific wavelengths. And that actually tells us what data points correspond to which wavelength. So right now the data that the telescope is taking are for flats. So it's basically removing the artifacts. Let's see if I can show it a little bit better here. Yeah, so it's basically just looks like a bar right here. Yeah, this isn't really meaning anything, so it's all buffer A, because buffer C is like a subtraction of difference. So Brian, I'm also thinking that do we need to clear the buffer for the difference images? Or does that just go away when you take a B pair?
It's like a C buffer.
Yeah.
Yeah, it should update when you do an AB pair.
Okay.
The C buffer is the A minus B subtraction.
So it just got done taking the flats. So the data themselves, the unprocessed data are in this A buffer right here. And so that's for the flat field correction right there. Now I think it's going to take some lamp. Actually, I'm not sure. I'm not 100% certain, but I think it's now doing the arcs. So it's turning on. Use argon, xenon. Yeah, these are the lamps right here. So we're. Do you know what chemicals we're using? Is it argon or xenon or what kind of? No.
You're gonna have to talk to my panel. They might not. So.
Yeah, it's all very mysterious. Let's see if I can show you a little bit what it looks like. So I'm gonna draw a line cut through this. It's like line, like that after, yeah. There we go. So yeah, this is kind of like what the spectrum of the chemicals that we're looking at. So it has a bunch of emission features, and each of these we know the exact wavelength position of where each of these emission features is located. So we can now use that to calibrate our data. So when we look at an asteroid or a star, we know which features correspond to which wavelength. Okay, so I think we're done with the cals. So we're going to go to observation mode. I'm going to Hey, I'm gonna go back to guide dog here and make sure that we're still on track here. So I'm gonna do the sync rotator, the parallactic angle again. I'm just gonna start the process all over again. Okay.
Full screen.
Oh, are y'all pulling up stuff on those monitors?
Yeah, I'm gonna pull up the instruments full screen over here.
Oh, cool. So yeah, we have some monitors over here for the people here to look at the what's going on in the instruments. So y'all on Zoom can see what's going on here. And now we have some monitors over here so that people here can watch what's going on over there.
Thank you. Yeah.
Thank you, Brian.
Yeah.
All right, so I'm gonna put the target back into the slit. Well, I want to stop guiding actually.
You say by analyzing the wavelengths that come in from that star, you can kind of set a baseline for identifying true stars or asteroids?
Yeah, so what we did is we actually closed the instrument up and we took a spectrum of a neon or xenon or argon gas, and it creates these features right here that are like standards. So we know exactly where each of these features is located from a catalog of spectral features. So now we'll be able to know what the wavelength location of all the features of our target are.
Put in the argon lamp, learn what argon looks like. So that you know what argon.
No, it's like that.
All right. Okie dokie. So, all right, I'm gonna draw a line here. There we go. We're gonna offset the telescope. Then we're gonna go to guiding. Here we go. All right, looks like it needs a little bit of help here. Oh, I got it. Okay, good. Pulled it right under that slit there. All right, so now we're gonna go back and start taking data. Got our AB pattern here, 5-second integration. Here we go. Now we'll see what an actual star spectrum looks like. Actually, wait 1 second. I want to do 2 coads just to be safe. 2 coads in 5 seconds. So in about a minute here, we'll have our first AB subtracted star spectrum. Let's see. Yeah,
Does the star spectrum help us glean the distance of the stars away?
I'll tell you in a second here. So one moment. So if I go here, I draw a line there like that, actually. Over there. So there's our first AB pair. So that's looking pretty good. Yeah, so here's our first spectrum right here. So this is a spectrum of a star right here, uncalibrated. So the water, so the atmosphere, the Earth's atmosphere has water right here. So this is from 0.7 microns to 2.5 microns. So the Earth's atmosphere has very strong water absorption features of 1.5 and about 2 microns. So that's why we have these huge dips right here. There's also some water features right there as well. But when you calibrate the spectrum, these are called telluric features. And you can remove these telluric features and you get you get the actual true spectrum of the star. I'm gonna draw, so it looks like looks like the signal is fine. We don't want the signal to be too bright. Here we go. All right. So one exposure is about 5,000 counts because we did 2 coads. The nonlinear regime is around 10,000 counts. So this is actually pretty good. So yeah, that is a stellar spectrum right there, uncalibrated. So when you're measuring the spectrum of a star through the Earth's atmosphere, you're not only getting the spectrum of the star, you're also getting the spectrum of the Earth's atmosphere. So you have to do some techniques to remove the Earth's atmosphere, what we call telluric features, from the star's spectrum. And yes, so measuring the spectrum of a star, we can see if it has any features that would be abnormal compared to what we think that stellar class is. So stellar spectra vary as a function of temperature. And I'm not a star expert or anything, but stars can have differences from each other, depending on their temperature, as well as if they have a different composition. Like if they're polluted stars, like let's say a planet or an asteroid or something else, a star, it can be a polluted star, and its spectrum can look different from other stars like it. So I think we'll be done in about a few seconds. Do you want to go to our first asteroid target, Brian? So our first asteroid target is going to be 37274, and we are done. So I'm going to stop guiding on guide dog. So this one might be a bit difficult, so I might skip it and do, we don't see it in our first go, might skip it and go to a brighter one, but the conditions are really good right now. So even though it's a bit faint and at a high air mass, I'm thinking we can probably still see it. So we're going to look at an asteroid that is a visual magnitude of 17. The human eye can see stuff that's around 5, visual magnitude of 4 to 5. So this thing is like a million times fainter than anything you can see with the human eye. Yeah.
Yeah, what in order of magnitude, when you go from like 8th to 9th magnitude, how much is it then? Like 100 times or something? One magnitude.
So that is 1. So that is 10 to 1 divided by 2.5. So I think that's like 3 or 4 times.
Okay.
Can I ask a question, Bryce?
Yes.
All right, so very quickly, you mentioned that you're maybe going to explain spectroscopy to us a little bit. You mentioned emission lines. Could you maybe tell us what absorption lines are and what we can expect to see from the spectra of an asteroid?
That's right. That's right. So asteroid spectra look very similar to our sun, or look very similar to the sun spectra, because basically they're reflecting light from the sun. They're kind of like a mirror in space. So when you reflect light from the sun, you're basically going to be getting the sun's light when you observe their spectra. However, asteroids contain chemicals on them, minerals and other kinds of deposits that can absorb light in different ways compared to the sun's light. So what we are doing is we are looking at the spectra of asteroids that have had the solar spectrum removed from them. It's basically we're looking for the spectrum as a function of wavelength that is showing us the difference between the sun spectrum and the asteroid spectrum as a function of, as a function of wavelength. So the different absorption features tell us what the chemical composition of the asteroid is. Are you taking some test images with Morris?
Yeah, just one test in course. I think we should see it.
Oh, the shutter is closed. Yeah, I forgot to open the shutter.
Oh, the Morris shutter?
Yeah. Sorry about that. So MORS is an optical camera that kind of like helps us set up the spectrograph for faint targets. So that star we just looked at is a magnitude 15 object. Sorry, it was a magnitude 8 object. So it was 9 magnitudes brighter than our asteroid. So it's very easy to see. But our asteroids are a lot fainter, and we can't see them with just a near-infrared camera by itself so as easily. So to compensate for that, we use an optical camera that is connected to the near-infrared instrument that kind of helps us lock on and find our target. Did I get something wrong here?
For sure, it's gonna be that one here in the center.
Oh. Let's see. Let me, yeah, so now we have to play the game of the finding the asteroid. So now I'm trying to check the ephemeris because on my end, because I am not sure. If you see what I wanted to see. Sorry about this. Give me a few minutes. Yeah, I wonder why the Minor Planet Center is saying this is magnitude 19.6. Very bizarre. All right, well, let's see if we can diagnose this really quick. Oh, it's just way off. 527, this is 04, 25. All right, well, I guess we'll go by the JPLs. Do we have a window on here that tells us the RA and deck of what we are? Okay, so 1303, so that's at minus 30. Okay, so that's looking about right. It says May 27th, 2024. So I don't know what is going on with the Minor Planet Center's ephemeris generation tools. Are we using we're using JPLs, right? Yeah, so there's a huge discrepancy between the Minor Planet Center and JPL. I don't know what's going on there. So I'm going to look at our date time. So it's right now at 6:40 UTC, May 27th. So it's actually May 26th local time, but we are 10 hours behind universal time. So when I say May 27th, I'm referring to universal time. So right now it's 6:40 universal time. I'm going to pull up a finder chart here. Sorry, I can't show this to you on the web here. Let's see. So I guess we can continue to take. Is it all right if I do ABB pattern? I'm going to do an ABB pattern. There we go. So yeah, I agree with you, Brian. I think it is that brighter one right there.
That's normally where it pops up in Mars, but I'm pointing to it.
All right. So I'm looking at a reference catalog of what the sky looks like. And so we can see the two stars here. And there's some weird thing going on right there. So I'm gonna look at the ESS. Yeah, there's something else going on there. So I think this is our asteroid. That's gotta be it. I think that's gotta be it. So yeah. We'll do a double check. And so this is moving west. So that's good. And it's moving west and north. So it's moving northwest. So it should be going in this direction. Okay. So I agree with Brian. I think that is our asteroid. And I'm going to start doing the setup. I'm going to use Brian's cheat sheet for using Morse. So you take an image with Morse, which we just did. We'll do it again just to be extra safe. And so the way this works is you want to set up guiding with Morse, and you don't actually guide with guide dog. So you guide with Morse. Morse is going to tell it's going to tell guide dog how to put the asteroid under the slid, so we can take an asteroid inspector. All right. So there we go. So I'm going to click on the asteroid. I'm gonna, for offset, I'm going to do GA. I don't know what GA. Do you know what GA does?
Yeah, that guy took the box.
Okay.
So did you hit GA?
Yeah, I did. So I'm gonna go to faint mode. And I'm gonna hit go here, so we should be guiding.
Yeah, I mean, there's a chance too, you could probably decrease that eye time because that's where it's coming in so bright. The shorter the eye time on guiding, generally better.
So I should do like 10 seconds, you think?
Yeah. I think it's get over 10, I'm sure.
It's not gonna let me change the eye time while it's
I just stop guiding.
all right. GA. There we go. All right. Okie dokie. So it looks like it's got this green box. It doesn't want to guide on the asteroid. It wants to go on this little green box.
Yeah.
But I clicked GA.
Again.
Pretty sure I did. GA stands for good asteroid.
Is this asteroid in the asteroid belt between Mars and Jupiter?
That's right. It is in the asteroid belt. It's in the inner portion of the asteroid belt. When we get everything going here, we'll have about 20 minutes, 20, 30 minutes looking at this asteroid where we have some downtime and talk a little bit more about what's going on. Science-wise. Oh yeah, y'all got the good blow up image there. That looks great.
Guide dog's the one that we saw also in front. This,
Yeah, so that blue box, that's SpeX.
Yeah.
And everything, SpeX, Guide Dog and Big Dog are both inside that.
oh,
Morris, I think, is a little, I don't know if we pointed out Morris, but yeah, it's like next to SpeX. It's like a small,
right?
yeah, it's a tiny little thing. The other one we pointed out was Mercy. So that one was a little bit further away. That one's like, medium sized. But yeah, Morris is also pretty tiny, sits right next to SpeX.
All right, we're good.
Oh, great. It's good. It's doing great. So this is exactly what we want to see right here on the V buffer. So that cross is where we want the asteroid to be, and that purple square is where the centroid of the asteroid is. So it wants to put that square right on top of the that green cross. Okay, so now that we're on, in Guide Dog, set parallactic angle. So we're going to sync the parallactic angle on Guide Dog. I sometimes call it little dog because we have big dog, but yeah, that might be confusing to people. So all right, so now we set the parallactic angle. Now we hit auto guide box setup. So that gets it going up and down because what we're doing is we're doing A/B pairs. And I'll explain a little bit. Right after we get this all going, I'll talk a little bit more in depth of what we have going on here. So I think I time, we're going to do like 20 seconds I time. And take an A/B pair in basic mode. All right. Go. Yeah, so SpeX is a little bit more well, all spectrographs are all set up like this. It's a little bit more process intensive. But once you get it going, it works very well. So we're guiding on Morris, but we're going to tell Guide Dog where to put the slit. So we can take data with Big Dog. Big Dog. All right, so now we are taking an A/B pair in window 2, set buffer to C. Now I get to draw. Okay, so I think that's our A/B pair. And I think that's going to be the asteroid right there, if I'm not mistaken. So now what I have to do is I have to click on this little guide box thing here. Actually, I want it to go away. So now I draw a square. So I don't hold down the shift, I just right click. There we go. I draw a square on top of the asteroid. And there we go. And now I go to Morris guide box adjust. I want this to be the buffer C. It's going to be faint. Calculate those offsets. So now it's kind of hard to see, but if you look on you can see it over there on the big screens. So it drew a green line from the asteroid to this top square. And that's what we want. And apply offsets of TCS and more. So now it should be putting that asteroid right in that top box, right where the slit is. And hit done. And now we're going to go to guiding, but we want correct TCS off because we just want to look at it just to make sure it's on the slit. So now I'm going to hit go. And we're going to make sure the asteroid is on that slit. And it's probably going to be fake mode. Here we go. Let's get a refresh picture of this guy. Oh yeah, it looks still looking great.
Yeah.
I think the moon is starting to rise. So yeah, you can see the Milky Way there.
Oh, what?
If y'all want, after we're getting this all set up, we can go outside and look at the stars. Y'all want to do that?
Absolutely.
Oh, hey, I gotta show them the goggles. I'm gonna 1 second.
We don't have NVQs anymore.
Oh, we don't have the red goggles anymore?
No, somebody stole them.
What? Oh, actually, you know what? Hold on. I think I got a story for that. They might not be stolen. They might just be misplaced. Because last time they were here, we put them in the corner over there. So no, not the night vision goggles, but there's like these red goggles.
These little things right here.
Oh.
Oh yeah. Yeah, I put them last time. Okay, so we'll take turns here. So you go first, George.
Okay, where do I
So
go?
wear those, and you got to wear them for like 10 minutes.
Okay.
So what's going to happen is, so let me So we're guiding on the asteroid right now. So I'm gonna get this all set up. We're gonna take 6 cycles. So we're gonna test this out first. So this is gonna take about 5-10 minutes just to make sure we're doing this correctly. So yeah, put those on.
I'll put them on right now.
Yeah, put them
Okay,
on right now.
Right now.
Okay, so we've got these red filter goggles. So what these red filter goggles do? Yeah, they're kind of tight.
I got it forward mode later, it's all right.
There you go. So we got these red filter goggles. So they're only gonna let like red light in. So you ever like stood in like a dark room for a while, your eyes get adjusted and you can start to see better night vision. So what's happening right now is we're doing that to his eyes, but only for the blue light. So right now you can still see red light because it's it's a red light filter. So you're only letting in the red light, but the blue light is not being let in through there. So only your red cones are seeing stuff, but your blue cones, it's basically being in a dark room. They're not going to be exposed. So when you go outside, stars emit light, mostly in blue light. It's going to make the stars pop out like crazy.
Oh, cool.
So yeah, so that's what you got to wear for about 10 minutes.
All right.
So that lets your eyes get adjusted. So
All right.
we'll take turns.
Yeah.
We'll maybe do it for 5 minutes. 5 minutes should be good enough. And then we can go outside and look at it, and then take turns. Getting our eyeballs adjusted.
Sounds good.
So yeah, it looks like the moon's about to rise. Yeah, that is the Milky Way.
Where is the moon?
You can also see the Southern Cross from here as well. The moon, let's see where the moon is. I have a diagram here that shows star tracks. This is May 27th. So the moon is going to rise in the east.
Yeah.
So
It's on the right.
yeah, so it's going to be on the left here. This is east, that's west, that's north and south.
Okay.
So the moon is going to rise. The moon rises at around 11 o'clock local time. So we got a few hours, so we'll be able to see plenty of stars. So right now we're taking our first cycle here. Yeah, we're doing pretty well here, I think. So I mentioned we're taking AB pairs. So each image we take is an AB pair. So we take 2 images at a time, but every time in that pair, we offset those images by about 10 arc seconds. And the reason why we do that is because the sky is so bright that you can't see anything. So you see how like this is all, you have the white and the black. So the white is the A pair and minus the B pair. The B pair is the detection of those in the black. Yeah. So when you subtract the A from the B, you're subtracting the sky background. But if you didn't do that offset, you'd just be subtracting the star from the star, and you wouldn't see anything. So we have to do this AB pair stuff so that we can actually see what's going on. So right now, like this is the A buffer for our asteroid. So let's see. So I think it is. I think we do have the slit on the on our target, but it's hard to see. It's really hard to see. Yeah, it's really difficult to see here, but it looks like, so this cross is where the slit is, and that square is where our asteroid target is. So I think it is guiding. It's guiding really good on Morris. Let's zoom in a little bit here. I don't know if I can see that. Display options. Oh yeah. So this is like so you can see the trace from but this is just a single A image. So now we have about a few more minutes to go, a minute left, and we'll have the B image done, and then we'll subtract the 2 together, and we'll put it here on the buffer C. So we'll see the trace for the A in white and the trace for the B in black. And so right now we only see 1 image. And so these telluric lines, those are the atmospheric spectral lines. But you kind of get a rough subtraction. It's not perfect. You kind of get a rough subtraction when you subtract those 2 together. That's what allows you to see the trace a lot. You can see it. So right now it's just like barely noticeable. So that's what those lines are. It's a spectral trace. So it's basically just looks like a line. So what's happening is a camera, you see the star, it's a blob, right? But when you sit lying through a spectroscopic slit, and it's also going through a prism as well, you're spreading that light out into a rainbow. Think like the Pink Floyd album, you know? And you're spreading the light out into this line. Well, what happened here? Need an AV pattern. Auto. Oh yeah, it's there. It's just a bit faint. So we have about 10 more minutes on this object. I think we're doing pretty good here. So we're looking at the quick look.
We run a 5 on 10 off schedule.
No picture.
So 5 minutes on.
Let me try and figure out here
Well,
exactly
we would
what's
be
going
doing
on
that
with a
the
quick
person
look.
Operator. Or type of thing.
So right now I'm doing data verification. So the individual AD pairs look great. But now I want to look at the compilation. And I want to get kind of a rough idea of what the signal to noise is.
I was ACC, I got an associate's for.
So I have this tool here that lets me see the signal to noise. So I sweep it over the spectrum here, looking at.
I
dog.
always was a door mouse. It's fine.
It looks a little bit lowish on the long end, so I might do some more integrations here. We're about 2 minutes to go on this asteroid. Let me check in with Brian here to make sure we're on track to go to our next target. I think I'm going to skip this next our second target because it's a little faint. And just going from the performance from this one, I think better go to a higher altitude target. Let's see here. Let me see. So that one is V of 16.4. We might come back and do that one later.
What's it? Later. Yeah, isn't it a lot better? Yeah. Try to. Yeah, I'll try to.
Then we have 996. Let's see here. 806, but we won't do that one. So that one's done.
I've been an operator officially for like 4 days.
Oh,
But I've been driving.
Oh, this is your new operator, Brian?
I was just giving.
Congratulations, Brian.
No, they gave me the title and no raise.
So Brian, you are. I'm sorry, you are now an official operator, and before you were what was it what you were before?
We created an assistant telescope operator position. So that hopefully they'll continue to promote these things, but they hired a master. Got an associate, so the idea was that on-the-job training is far more valuable than any sort of
So sorry to interrupt you, Brian. We're almost done with this one. Are you ready for the Henry Draper name of the next star target?
So far.
It is HD 131715.
Some catalog, I'll search it.
Yes, HD 131715. So we are looking at Henry Draper stars that are solar analog-like, that are similar in their spectra to solar stars. The reason why we do that is because we are looking at asteroids as our primary target, and asteroids reflect a lot of solar light. So we want to remove the solar spectrum from the asteroids, and we do that by observing solar-like stars as a proxy for the sun, because we can't actually observe the sun. With this telescope, you would not want to do that.
I think
This
they-
telescope does.
I think we did that one time, Bryce.
Really?
Yeah, they hung like some massive vortex or something in front.
Oh.
Drones or something like that. Bro, I don't know. Somebody's telling me a story one time. They did. We did observe the sun.
And it didn't cook the telescope?
No, because they had a massive sheet hanging outside.
Oh.
I don't know who told me. I gotta go visit that again.
Well, this telescope is very unique on Mauna Kea because it's the only telescope, near infrared telescope that operates 24/7. This
Well,
telescope can operate 24/7.
there, again,
So they observe Mercury, they observe Venus. They do all these daytime observations of planets. So it can observe during the day.
In addition to measuring the spectra here, does this telescope specialize in?
Oh, sorry, I'll turn off the guiding.
oh, yeah, I already stopped that.
Oh, thank you.
Can we get like high res of the asteroid? Can we like see it zoomed in?
So right now, the pixel scale of this camera, I think it's like 0.2 arc seconds. I think it's 0.4 arc seconds. Pixel scale of these cameras is 0.2 arc seconds. The seeing is 0.8 arc seconds. So that's the best resolution we can get to the ground.
Right there.
Yes. And that's really good because a lot of observatories, like you'd find in Mexico, New Mexico, Arizona, where a lot of other telescopes are, the seeing is about 1 to 2 arc seconds. So we made a mission called Stardust in the 2000s, which rendezvoused with a comet called Bile 2. And are we on the asteroid yet?
Sorry, I was pointing up next door. Let's try taking it close right there
Oh, that's it?
Yeah.
All right.
Yeah, I pointed up, back over there, took an image of Mars. Sorry, I forgot to hand it over right there.
No worries. So I'm gonna take another image, I guess.
Yeah. Update it. But that should be your asteroid right
Yeah, I think I agree.
now. That's it overreads. Yes.
Is that it where your cursor is, Bryce?
That's it. So I'm gonna draw a little square around it. That's it right there, that blob right there. And I'm gonna click on GA. And I'm gonna go to guiding here and get this thing guiding on the asteroid. GA. Uh-oh. Hello, Brian. It wants to do the weird thing where it doesn't want to put the square on the.
This is more important. Stuff like we're gonna stop guiding, do a little drag, offset,
Oh, there you go.
and then go on guide.
Oh, okay. Little trick there.
Yeah, it should pull it in, I think. Yeah, it's like
There you go. That looks good. All right. So we did the GA.
there's a little bit of misunderstanding.
Now we're gonna go over to Guide Dog. And we're gonna do a 25-second animation. We'll do an A/B pair. So this target that we're gonna observe now is B of 17.1. So it's similar brightness as our previous target, but this is at a much lower air mass. So we are at an air mass, let's see, where is it on here? Air mass of 1.05. So that's, previous one was at 1.5. So that's a much lower air mass.
But it's allowed. They apply for time.
How do you determine which asteroids you want to look at?
That's right. That is a lot of the troubles coming up with a target list. I will tell you that in a second. I need to seek the rotator to parallactic angle.
So right when I went glasses on, I was like,
Well, you're supposed to go outside and take off the goggles. That's what makes the,
no, yeah.
oh, you did?
I was outside with them still on when I took them off. I didn't have glasses on.
Oh,
And I was like, and then I put them back on.
Oh, yeah. Yeah, it was pretty crazy.
Right. Just. Specs can see, like, specs can see a certain amount, right? I shall.
Uh-oh, and Brian.
Yep.
The, it looks like we're losing the guiding again. Oh, wait, no, I don't know what happened there.
Oh, it switched to BB. Are we
Ah,
guiding D and Mars? Yeah, we are. Yeah. That was it. That was just a beam switch. And then pull it back.
all right.
That's just the limited wavelength. I should.
Let's see here. Guide box setup. Oh, come back. There we go.
Right.
Sorry, I don't want to stay.
That.
All right. Oh well. I'll do this. I'll draw the square around that one right there.
Let's go back. What I learned.
Offset. Morse guide box just calculate those offsets. Apply a TCS. We're guiding now, so I'm gonna start taking some data. Yeah, so you're talking about how to come up with the target list. So coming up with the target list, that's the tough part. So coming to the telescope, and setting this all up and observing, that's one thing. And pointing a telescope at a target, standard star, and pointing at an asteroid is another thing. But knowing which asteroids to look at is a very different thing. So I have these this method that I use, data analysis method, that I use to find collisional groups of asteroids in the main belt. And I have a way that basically tells me which asteroids I think are gonna belong to the main belt family, collisional family, and which ones are just the background. So I want to study asteroids that were recently involved in a collision within a few billion years. And I think this is a real collisional family of asteroids that were once a part of a giant asteroid that broke up into a bunch of little pieces. And so using this data analysis technique, I've identified asteroids which I think are collisional fragments of this original parent body. And I have a list. I have a list of all the asteroids. And so I'm observing them when they are bright and observable from Hawaii. And I have about 400 or so asteroids. And tonight there's about 10 or 15 of those that are bright enough and observable from Hawaii, where I am. So I'm just going down my list and observing those asteroids which are observable.
Oh, that's awesome. That's awesome. And so, could you explain I know there are different types of asteroids, but I'm going to kind of go in a different direction. I'm curious about why is it important to know the rotation rate of asteroids, especially of the larger ones?
So yes, that's right. Asteroids are not stationary. They're not fixed in space. They orbit the sun. But like our Earth orbits the sun, just as our Earth orbits the sun, but also like our Earth spins about its axis. So do asteroids spin about their own axis. And so the Earth has a rotation period of 24 hours, but asteroids have rotation periods that can vary quite a bit between tens of minutes to a few seconds for the smaller asteroids. They can be several hours or more for the larger asteroids. And for asteroids that are 10 kilometers or size, larger, they can spend on the order of several hours to 80 hours. So much slower than our Earth's rotation period. So it's thought that when asteroids formed, they formed from a cloud of dust particles. And due to conservation of angular momentum, when they collapsed from a dust particle cloud into a smaller smaller radius, but more dense asteroid body, they started spinning. So getting the rotation period of asteroids that are large tells us something about the original rotation rates that they had when they formed, after they collapsed from a cloud of dust particles. Another thing that they can also tell us is they can tell us stuff about the material properties of asteroids. Because the asteroid's critical spin period is related to its rotation period. So it's the critical, so for the typical density of an asteroid, which is about 2 grams per centimeter cubed, the critical rotation period, the rotation period that it would have before it would start spinning so quickly to break up, is about 2.5 hours. And so observing asteroids and measuring the rotation periods allows us to understand roughly what their material properties are. So if we find asteroids that are spinning faster than that or spinning slower than that, it gives us an idea of what the critical density of an asteroid has to be for it not to break apart due to its centripetal effect of the asteroid spinning and starting to shed material at its surface. So there's kind of two ways. It tells us about how asteroids formed, as well as the density, the physical properties of asteroids themselves.
Here on the backside, old South.
So we just got our first AB pair. It looks pretty good.
Just get down. There's no speed bubbles anymore. We come out with CNC trucks.
It's looking pretty good so far.
They're so stable and.
So I think this asteroid looks the data look higher signal to noise than the previous asteroid.
We used to be getting the cash trucks that would.
So let's see.
You
You can see here, right here on the D buffer, you see it. That's the cumulative.
70 miles an hour.
Just look at the C
Slow.
buffer.
People are starting to do.
So we just took our first AB pair. So that top trace is the trace from the A, and then the black one is subtracted, the residual from the B pair.
Yeah, so.
So what we're doing is we're measuring the signal to noise here. It's about 10 or so, but it's a square root of 2 higher because we're only measuring the signal noise from one of these traces. So we're taking these into B pairs. So it would be about 14 right now. And we're going to do 6 cycles. So at the end of 6 cycles, we'll about more than double the signal to noise. So I'd say we get around a signal noise of 30 or so in the final combined spectrum here. So maybe we'll take some more data